What's up, YouTube? Let's go. So today we're going to be talking about some beautiful math, as usual. Today we've got the triangle numbers, which I'm going to introduce, and I'm going to be motivated partly by this really nice identity about the current year 2025. So let's go. But first, before we do that, let's recap what we did last time. So, I'm going to create my YouTube short right now. 3, 2, 1. Hey, what's up, YouTube? How's it going? So, last time that we did a stream, we worked on skip counting around the clock. This is one of my favorite topics that I like to show little kids. And it's kind of hard to create like a analogy around it, but basically, what are the patterns in the clock? Like, if you skip count around the clock by 12, you're always going to get the same number, right? Or if you skip count by threes, like 12, 3, 6, 9, 12, 3, 6, 9, you're never going to see the number 1, right? This is a pattern that I think a lot of little kids like realize, and they think that's kind of cool, but like, is there something there? Like, I don't know, that's kind of nice. I remember thinking that when I was young. So if you go back to the old stream that I did last time, I showed how these generate like kind of like little like sub-clocks, and they repeat in a cycle. So these are called cycles in mathematics. Basically, this is the beginning of modular arithmetic. So what we're essentially doing is counting, or doing addition, mod 12. And the question is, are there any numbers that if you skip count by that number, will we get to the number 1 from the number 12? Well, yes, because we can count forward by 1, of course, or we could count backward, like 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Are there any others? Yes, it turns out that counting forward by 5 is also the same as counting backward by 5. Counting plus 7 is the same as counting backward by 5. And those two do see the number 1. So it's pretty cool stuff, I promise you. Essentially, we notice the pattern that in the clock there is subtraction as well as addition when we're working mod 12. Cool. So go back to the stream if you want to go see all the details, or while I explain it a little more carefully. But we left this like with, what if the clock had 13 hours or 14 hours or 123 hours? I like to call these alien clocks. What kind of patterns are in alien clocks? Thanks for watching, and see you in the stream sometime. We are currently live, and I'm going to try to stream every day. Alright, thanks. Bye. Okay, so now we got our recording done. Let's go. So, what's up, everybody? Anybody out there? I see we have one viewer. Let's freaking go. That's awesome. Okay, so this is a new channel. This is a brand new mathematics channel where I'm going to be trying to show what I think is beautiful math. I think that this is quite beautiful math, and I want to show this to y'all. All right, so what are we doing again today? We are going to be doing triangle numbers. Okay, so what is a triangle number? I like to show it this way. So what is a triangle number? In grade school, we often learn about arranging dots in rows. Nice, neat rows of dots. This is 2 times 4. 2 times 4 is 8, right? And we notice some patterns like, oh, you can't arrange 3 in a nice, neat grid, right? So 3 is prime. The only factorization of 3 is 3 times 1 equals itself. But the world is not equal. Like, there's no equality in this world. What if we listed 3 as 3 equals 1 plus 2? Or what if we did this neat stair step kind of thing, right? We're going in increments. So how many dots do we have here? 3 plus 3, we've got 6. 6 is 1, 2, and 3 added together, right? So these are the triangle numbers. I hope you see the pattern. So what is the next one? Well, it's going to be 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. We already know that the last triangle number was 6, so we just add 4 to that, and that is 10, right? And these create these nice little triangles if you arrange the dots in rows, right? Cool. There's not really any good reason to draw these lines. Let's just get rid of those lines. There's no good reason. But, yeah, you see that those are triangles, right? Great. So let's keep moving on. Now, there's a famous story about a mathematician named Gauss. And this guy, his entire class was acting up or something like that, and the teacher gave them a punishment, like, so that they would calm down and relax and stop being so noisy or something. What is all of the numbers? What is the 100th triangle number, essentially? So, that's going to take you a long time if you just add it up by one. Well, Gauss was a freaking genius. And when he was like 3 years old or something, he looked at the blackboard and he saw that and was like, And he immediately, in a moment's notice, noticed, well, you could write it down backwards, right? Whatever this number is, I'm going to call it T100. Well, you can add numbers backwards, right? And it's the same thing. So, what if you add T100 to itself? The 100th triangle number. Well, in each column, we're going to get 101. Notice that the first column, 1 plus 100 is 101. The second column is also 101. And, well, how many columns are there? There are 100 columns. Right? So, then, therefore, 100 times 101 is 2 times T100. Then, therefore, our answer that we were looking for, which I'm now going to write this way because we have a little more space or something, is 100 times 101 divided by 2. Voila. Beautiful. Here's that. And who cares exactly about what the number is? The point is, this is so much faster. We just have a multiplication and a division. So it's just 2 operations, 2 little tiny math problems that you have to solve instead of 100 math problems, like 100 operations, 100 steps if you do it this way. This way, we only have 2 steps that you have to do. So that's pretty cool. But if you're curious, 100 divided by 2 is 50. And 50 times 101 is going to be 50, 50, I believe. Let's double check about that. 101 times 50, I'm pretty sure that this is right. 0, 1 times 5, 0 times 5, 1 times 5. Yep. So, the iPad is off camera. I wonder if it's better to do it this way. Anybody in the stream? How's it going, world? What's up? I wonder if it's better to have the iPad vertically this way. Then that way I know for sure that I'm not clipping at any point. Can the iPad shrink? Oh, what? Okay. I think this is good. I think that this is fine. It doesn't need to be so large horizontally. Feedback is an absolute gift. If anybody has any suggestions for how I can make the stream more interesting or visually better or anything like that, I'm all ears. Okay, so that is one example of a triangle number. And if you go back and think about this, there's really nothing special about the number 100 here. This could be n. And this could be the nth triangle number, right? Well, if you did that, this would be, each of these would be n plus 1. And then the formula, Tn, is going to be n times n plus 1 divided by 2. And then the rest of the reasoning, the rest of the argument is exactly the same. So that's a pretty neat little math fact if you ask me. Let me just clean this up a tiny bit. n plus 1 divided by 2. Beautiful, beautiful, beautiful. Let's move that right there. Okay. So that's step 1. So check mark, we've introduced the idea of triangle numbers. Now, what about this identity that we have? 2025 is 1 cubed plus 2 cubed plus ... 9 cubed. And it's also 1 plus 2 plus ... 9 squared. How can we check if that's true? Well, we can just calculate it, I suppose. Now that we have this formula for Tn, then we want to see, does 2025 equal 1 plus ... 9 quantity squared? Well, remember that this then would be the 9th triangle number, which now I want to write as T of 9 in like kind of a function notation. Quantity squared, right? Well, so I have a question mark in the previous line, which means that we should start a new line and start from either side, either 2025 or from the right-hand side, and try to make a bunch of steps to get to the other side. So, T of 9 squared would be, based on this previous formula that we had, it would be 9 times 9 plus 1 divided by 2 quantity squared, right? Well, 10 divided by 2 is 5. That's what I meant to say. 5 times 9 is 45. So all we have to do now is just check what is 45 squared. 45 squared, let's do it a couple of different ways. First, let's do it kind of the simple way. Let's use a different color just to show that this is like a side calculation. 45 times 45. Let's do it the simple way. 5 times 5 is 25. 4 times 5 is 20. 5 times 4 is 20. 4 times 4 is 16. Plus 2 is 18. 5, 2, 0, 2. Woo! Hooray! This is 2025. Cool! Heck yeah. So, making progress. We have shown officially that 2025 is 1 plus ... 9 squared. What about the other one? What about this thing? For fun, you could practice your cubing, which not everybody knows their cubes times table. I certainly don't. I know some of them. Let's see. So now our next goal is 2025 equal to 1 cubed plus 2 cubed plus ... 9 cubed? Okay, so before I do that, I wanted to show a mental math trick of 45 squared. Can you do this in your head? Let's see. I like to think of something like this as 40 plus 5. 45 times 40 would be 160. Oh, wait, no, 6. Yeah, wait. 40 times 40 is 1600. 5 times 40 is 200. So this is going to be 1800 plus 45 times 5. 45 times 5 would be 225. And if you add those together, we get 2025. I don't know if I would be able to totally do this in my head. I think you could try. That would be one way. So I'm splitting up the number 45 as 40 and 5. And then I'm multiplying one part with 45 and then the other part with 45, right? You could also know this formula, that in general 2ab, let's move all this just a little bit right over here. You may also know this formula. So this would be 40 squared plus 40. Wait, let me write out. You can think of this as 40 and 5 squared. 40 squared is 1600. Let's write every step here. 40 squared plus 2 times 40 times 5 plus 5 squared, right? 40 squared is 1600. 40 times 5 is 200. Times 2 is 400. And 5 squared is 25. So this is, again, 2025. Those are 3 ways to solve that problem of what is 45 times 45. So, pick your poison, whichever one you prefer. In my head, I can do this one the simplest. Like, for mental math, I think that this strategy is a really nice one to practice mental math. And when I teach people mental math tricks, I think that that's a good one. So, often you can do a mental math problem like this faster than you can grab your piece of paper, faster than you can find a pencil or pull out your phone or ask ChatGPT or whatever. Oh, yeah, there's always another solution. You can always ask ChatGPT. All right, now 2025, 1 cubed, 2 cubed, 9 cubed. Just for the practice of it, I think it's worth... How many cubes do we know? 1 cubed, so this is 1 times 1 times 1 is 1. 2 times 2 times 2. Luna, my cat is chewing a cable. 2 times 2 times 2. Remember that this is what a cube means. 2 times 2 times 2 is 8. 3 cubed, I know, is 27. 4 cubed is 16 times 4, which is 64. 25 times 5 is 125. 6 times 6 times 6. 36 times 6 is 180 plus 36 is 216. Are these right? That one doesn't sound as familiar. 7 cubed, 49 times 7. 50 times 7 minus 7 is how I would think of this one. 50 times 7 minus 7. 50 times 7 is 35. So, 350, I mean. Hello, Luna. Hello, Loon. We've got my cat here today. So 50 times 7, 350, minus 5 is 343. I'm going to be proud of myself if we get this. 8 cubed will be a power of 2. 8 cubed is the same as 2 to the 9th. And the way I did that one in my head, and I know 2 to the 9th is 512. The way I did that one in my head is 8 cubed is 2 cubed cubed. And when you raise a power to a power, you multiply them. So this is 2 to the 9th. 2 to the 9th is half of 2 to the 10th, which I know is 1024. So half of 1024 is 512. I remember that one. 9 cubed. 81 times 9. 81 times 9 is going to be 720 plus 9, right? 721. 729. Did I get all these correct? I don't know. I think so. Now, we just did 9 problems, but then within each of those 9 steps to find the cubes, within each of those I had to solve problems themselves. I had to break some of those problems into smaller problems and solve these. So I don't know. I don't know exactly how many little arithmetic problems we just did, but it's more than 9. Um, Wild guess, maybe it's 18. Maybe for each one of those, on average, I had to do 2 smaller mental math problems, like 49 times 9. Rewrite that. Just rewriting it is kind of like one sub problem, like one step. It's like one extra step that I had to do it this way. So who knows? Maybe there were like about 18 um, math problems this way. Then, if we continued going the straightforward way, we would have to add 1 plus 8 plus 27 plus dot 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 729, which is 9 additions, right? Cool. This isn't too bad. I think that we could do it. We could do it just for mental math practice. Does anybody want to see mental math practice here? I've never tried this, actually. Doesn't seem so bad. Let's step 1. I've never tried this. Let's add all the hundreds places, right? And then step 2, let's add the tens, and then step 3, let's add all the ones. Instead of writing many different little like grid addition, like grids of additions, I think that we can do this one on paper not too bad. I'm just going to go ahead and write them backwards for the sake of clarity. 216 plus 125, 64, 27, 8, and 1. That was kind of large. Let's add the hundreds. 700, 500, 300, 200, 100. Okay? So I'm going to do 1 plus 2 is 3, 6, 11, 18. Right? So this is 1800. Let's use colors. 1800 plus, let's use green. Let's add the tens places. 2, 3, 7, 8, 10. So what is 10 hundreds? It's 1,000. That's wrong then. 10 tens is what I meant to say. 100. 10 tens is 100. Now, but what am I talking about? We missed a couple more. Oops. Okay. We got 100, 160, 180, and then we're done. So there's 180. And now, let's just add the ones places. 1, 9, 16, 1, 9, 16, 20, 25, 31, 34, 36, and 45. Okay, great. So we ended up with a 5 in the ones place, so I think we're still on track. Heck yeah. Um, let's do, again, the same thing. Why not? Add the ones places, and this ends up with a 5. Add the tens places. 4, 8 is 12, and no more in the first number. So 12. So basically we're carrying the 1 now to the hundreds places. So 2 plus 8 is 10, and voila, we carry that 1 to the ones place, and we get 2025. I want to rewrite this just so that it's more clear. Like, what exactly did I just do again? Let's do it the other way. This is 1,000 plus. There's no other thousands. We have 800. 800 plus 100 is 900. 800 plus 100. And then in the tens places, 0 tens, 8 tens, and 4 tens add up to 120. And in the ones places, 0, 0, and 5 is just 5. Now, do the same thing again. 1,000 plus the hundreds places. Hundreds places add up here to 1,000. The tens places add up to 20. And the ones places add up to 5. And voila, we did it, 2025. So, hooray, we have just seen, indeed, that 2025 is the sum of these cubes and the sum of the numbers then squared. How cool is that to me? Now, your mind, you might be going the same exact way that my mind is. That's like, is there anything special about the 9 in that identity? Is there something special about the 9, or is it like this one where that's always true? That's a great homework problem. That's a great thing to try to figure out if you can solve that identity is true for all numbers n. Right? So here is step 3 of this little mini lecture. Is this thing always true? I like to write it from the cubes first. 1 cube plus 2 cube plus ... n cubed. Does that always equal the nth triangle number squared? Well, if we want to see if this is true, we can see a table, the same way that we did in the other thing. N, 1 cubed plus ... n cubed, and 1 ... n squared. We could write that also as tn squared, but I don't know. I think it's simpler. It's just simpler to avoid that other thing. Um, but either way. All right, so what about when n is 1? Well, then this thing only has one column, right? It just has 1 cubed. And then on in this last part, there's also only 1 column in this dot 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 thing. So this is just 1 squared, which is 1. All right? What about when n is 2? What we're looking at is 1 cubed plus 2 cubed. And over here, we're doing 1 plus 2 and then squaring it. Oops, not cubing it, squaring it, I meant. Right? Okay, well, 2 cubed is 8. 1 cubed is 1. And 1 plus 8 is 9. Right? So over here, 1 plus 2 is 3. And 3 squared is 9. Right? Neat. 3. So let's see if this one works. 1 cubed, 2 cubed, and 3 cubed. 1 plus 2 plus 3 squared. 3 cubed is 9 times 3 is 27. 2 cubed is 8. And 1 cubed is 1. Right? 27 plus 8 is 35. 35 plus 1 is 36. 1, 2, 3 is 6. 6 squared is 36. Nobody in the chat today? Anybody like this? Anybody out there? What's up, y'all? Please let me know if you're enjoying this. I would love to build a math community of people practicing mathematics together. That is my goal here. So please let me know if you're enjoying this. I don't know if these need to be... Boop! Thank you. Thank you for following my directive. How's it going, Yo2Bear? How are you? What's up? Have you seen any of this stuff before? So we're talking about this. We're talking about triangle numbers. And we're talking about this identity about the square of a triangle number being related to the sum of cubes. In math, it's nice to have like a fancy sounding statement like that. The sum of cubes equals the triangle number squared. Like, this is the takeaway here. If you can just remember that sentence and get that in your mouth, it's something that's pronounceable, and it's something that can like stick in your head as like a mantra, and you can repeat it to yourself all the time. Like when you're taking a shower, the sum of cubes equals the triangle number squared, right? So that's what we're wondering. Like, is this always true? It works for 9. It works for 1, 2, and 3. What about 1 cubed, 2 cubed, 3 cubed, and 4 cubed? And what about 1, in the way that we're doing this, 1, 2, 3, 4 squared? 4 times 4 is 16. 16 times 4 is 64. 3 cubed is 27. So notice that we can just take the last one. Maybe we should have noticed this earlier. Let's see. Let's get this in a nice video format. Notice that this was the last number, right? And then we just need to add the next number. So why am I repeating all of this math? I know that all of this is 36 because I already did 1 cubed plus 2 cubed plus 3 cubed. We already did that one, so why don't we just add that there? Oops. Now we have 36 and 64, which is 100. Right? I think so. I think that's right. So this stuff is like really good for practicing your mental math, I think. Okay, so let's remind ourselves, what was this last triangle number again? Well, we think that it's always a triangle number squared, right? So just reminding ourselves that T3, this last number was 6. I mean, this isn't too hard. 1 plus 2 plus 3, I could have done that in my head at least. But I'm just thinking in the future when this is a longer list. 1 plus 2 plus 3 was 6. And then 6 plus 4 is 10. 10 squared is 100. Right? So, I think that that's enough for me to feel like, yo, I don't feel like checking these other ones for right now, but we already saw that this one works out too. I suspect that this is always true. I think that this is always going to be true. I think that this is a really good place to just leave this one, and next time we will see that it is indeed true, always. Next time, we're going to learn about domino math, also known as proof by induction. And then we will see that yes, this formula is indeed true by domino math. So thank you for watching. I hope you enjoyed it. If you enjoyed this, please hit the like and subscribe, and let me know in the comment sections, below, that you want to see me continue to do these, because that would encourage me to keep doing it, you know? So thank you for watching. My name is John. I am going to stream my classical guitar practice now, so let's go. Thank you for watching. All right, join me in the classical guitar channel if you want to hang out with me there. My handle is JC Practices, and if you want to support this channel, you can go to jcpractices.com. Best way is probably either to join the Patreon or to join a channel membership of my other channel. because I don't have channel memberships yet on this channel. Thank you for your consideration, and I hope you enjoyed. Thanks, y'all. Hit the like and subscribe, and take it easy. All right. Bye, everyone. Bye.